quick little note here, which won't take us very long. It's basically talking about uses of curved mirrors, and we're going to start with concave mirrors. All right. So remember, concave, in like a cave, and or also called converging mirrors. And the first one that I'm going to talk about here is obviously, you can see it there, solar collectors. And more general, it's for receiving parallel rays. All right. So we did an experiment at the beginning of the week last week, where if we wanted to find, all right, if we wanted to find the focal point of a concave mirror, we need parallel rays coming in, and we did it with 3 parallel rays. So when you have 3 parallel rays coming in, all right, it could be more than 3. When you have parallel rays coming in, that converging mirror will cause those rays to reflect and go through a particular point, which we call F, the focal point, all right? So for something like a solar collector, and I used to actually have an example of a solar collector. It looked a lot like this, but I have no idea where it went. That's what I was actually looking for in the cupboards. But if you take a mirror like this and you point it at the sun, all right, the sun is so far away, we can consider those rays coming from the sun as being parallel, all right? So they're coming in parallel to each other. So if you have a really far away light source, those rays coming in from that really far away light source are parallel, and they will focus at that focal point. If you then put something like, in this case, this device here is called a Stirling engine, all right? Stirling, named after the scientist who invented it. A Stirling engine is almost like a regular car engine, except it doesn't run on fuel, it just runs on hot air. So what happens is that parallel rays come in from the sun, they focus at the end of this particular device there, so that's the focal point right there at the end. It gets really hot, it heats the air in the interior of that cylinder, all right? That heated air has a little piston in it, and it causes that piston to go up and down, and a little motor runs, all right? So that's an example of how solar energy could be turned into kinetic energy, all right? I've seen also examples of really giant solar arrays where they have many mirrors, again, all focused at one point, and they use that heat to heat up a salt. It's not even a solution, but it's molten salt, and they'll use that to run turbines and then ultimately to generate electricity. On a smaller scale, right, if you had, you know, if you happen to live in Africa, where there's lots of sun and not a whole lot of, you know, maybe not a whole lot of trees, if it's drought stricken and you need to cook, you could have a situation like that where if you had a large solar collector and at the focal point, perhaps a place to put pots where you could then cook using solar collection, all right? So parallel rays coming in, they all meet at the focus. That's a lot of energy right there at the focus, and that results in some heat and ultimately the use of the solar energy. Another example of this, oops, let's go back, is a satellite dish. I talked about this earlier on. Satellite dishes, they tend to be parabolic instead of circularly curved, but they're close enough. And I'm going to use, again, my mirror as the example. You've probably noticed on all of your satellite dishes, if you have more than one, or perhaps you've switched one out, it doesn't matter which one we're talking about, that there is some device that sits out in front of the satellite dish. So there's some kind of receiver that's always out in front of the satellite dish. What would we call the point at which we position these receivers? Where are we going to put the receiver? What important point would it go? Yeah, you're going to put it at the focal point, all right? So put the radio receiver at the focal point of the dish. The parallel waves from the satellite will be reflected to that point. These are radio waves. So you don't need it to look like a mirror. It doesn't have to be mirrored in order to reflect radio waves. Even the big old satellite dishes that they had back in the 80s, they even had holes in them, all right? The wind could go through it, but the radio waves could not go through them, right? You might be asking, how do the radio waves reflect off of something full of holes? Remember, the radio waves are long, so you'd need really big holes for the waves to get through. Those little holes are too small for those big radio waves to get through, so they reflect off of them, all right? This one here, all right, is lined up pretty well right in the middle. So the satellite would have been positioned maybe in this position here, the rays coming in, all right, and reflecting off to that centerpiece right there. You'll notice that this guy is kind of down and off to the side. Now, even though we always, well, when we do our experiments, we point the mirror right at the source. If you were to have the light coming from up here, it would still reflect and focus to a spot down here, right? So not only is there a focal point here, but if I put a light source up here, it would reflect and focus down here. And that's what's happening with this dish here. You'll notice that this receiver is not right in front. So in this case, the satellite is probably up here, like this, with the parallel rays coming this way. And it's focusing and reflecting, and so they'll still go to that focal point. It's focusing and reflecting, all right? So you get this combination of the two. Either way, the parabolic dish or the circular dish would be used in order to catch radio waves. I assigned that kind of Mythbusters video, which don't worry about it right now, but they have a situation where on the Mythbusters, they take an old dish like this and they cover it with mirrors. They take little pieces of mirror and they cover it with mirrors, and they produce something that can produce a lot of heat at the end, right? So they turn it into a solar collector instead of a radio wave collector, okay? Now this has nothing to do with light, but it's a good example of the same thing. You've probably seen various sporting events like football where they have some guy standing off on the side with that plastic dish pointing at all the people as they're doing their talking to get ready. What they're doing there is they're attempting to catch the sound that's coming in from the people talking on the football field. And even though we're not talking about light, it works the same way. The sound waves coming in from a great distance away would reflect off of the curved surface and would focus at the position where the microphone is put, and you would then catch the sound waves. All of these are examples of catching parallel waves or parallel rays at the focal point. Now, in the past, I have taken the class outside and shown you how I can very easily start a fire with this mirror by just placing a piece of paper towel at its focal point. The sun is just coming up right now, so it won't be high enough in the sky to be intense enough in order to do that, so we're not going to bother, unfortunately. It's not even worth a try. It's a little hazy out there as well, so any little bit of cloud, kind of disperses that energy, so you lose the ability to do that. But it's cool. So all three of these examples dealt with collecting parallel rays, and parallel rays essentially come from sources that are a great distance away. Okay? All right, looking around, people seem to be in good shape there. What if we wanted to produce parallel rays? Remember, light is reversible. I've been saying that all the way kind of through here, which means if I put a light source at the focal point, that light will head back, spreading out as it does, right? Because light spreads out, and those rays that are spreading out from the focal point and hit the mirror will come out parallel. So that behaves as kind of a flashlight or a headlight. I wanted to have this lamp the other day, and I forgot about it when I was talking about real images. Oh, excellent. Blinding everybody in the morning. Nice. You might think that this kind of behaves the same way. We've got kind of a reflective surface, all right? But it's really quite dull in here. This is just aluminum. It's really not very shiny. So this surface here is not designed to be like a headlight or a flashlight. It's just to keep you from being blinded by this source like that. But if I were to do that, of course, oh, it's a nice early in the morning. It's great. This is awesome that it's Monday morning. I'm really liking this. This is good. But if I point it this way, all right, at me, and then I take my mirror, my big bright mirror, and then I place my mirror at the focal point, I can make a nice beam, and then I can do that. Oh, it's so much fun. It is so much. Oh, goodness. Oh, goodness. Aaliyah, just stop. It's so much fun, isn't it? I got to do it one more time. Okay, I'll stop. Now, notice here, if I do get it right, see there, I can get a nice bright beam on the wall. Isn't that awesome? What a great beam that is. Thank you very much. Very good. If I adjust it just by a little bit, I can actually get an image of the light bulb. All right, and this is what I was talking about the other day. Can we see what the wattage is of that light bulb? I think it's about a 120. Yeah, there's a 0 there and there's something else. Anyway, that's okay. You can see there's almost the writing there. Now, if I have it in this position, then that's not parallel rays, because parallel rays won't make an image, right? Remember, parallel rays, there's no image. So right there with the image of the end of that light bulb there, I don't have it parallel. If I bring it a little closer, there I've got the no image situation, and I've got a super bright beam. So essentially kind of creating a spotlight effect or a flashlight, all right? Okay, I was going to blind you guys one more time, but hey, you know, it never does get old, but we'll stop that. Okay, so flashlight or headlight, put the light source at the focal point, and you can generate a parallel beam of light. All right. Don't write that one down. Don't write that one down. This is a sound situation again. This is just like we talked about with the catching the sound waves. We can do the same thing with microphones. You can send the sound to the parabolic surface to make a beam of sound. All right, that can be used in a couple of ways. The military tries to use that. So let's say that you're battling somebody in some kind of a war scene. They can take a device like this, and they can make a beam of very bright sound, and it would be a confined beam, just like a beam of light, and they could fire that beam of sound at a particular person that they want to disrupt or affect. All right, even though there might be civilians nearby, they could send that beam of sound and just hit that one person with kind of a beam of sound and disrupt them. If you've ever been to a museum or perhaps an art gallery, and they use this technology, they sometimes use this technology in the ceiling. So when you get to a particular exhibit and you stand in a particular spot, you can hear the narrator explaining what the historical thing or what the art is about, and people to the a couple steps to the right or left of you aren't hearing it because it's just creating a little beam of sound that you're kind of hearing personally. So if you've ever noticed that type of scenario, that's the type of technology they're using. Again, that's not light, so I'm not that concerned. Okay, other uses for concave mirrors. Okay, whoops, click. One other use for concave mirrors, and we're still on concave, is that shaving / makeup mirror. And you know the mirrors I'm talking about. Actually, we did get a complete, they were at the dollar store the one year. We bought a bunch of them, but it's not worth me handing them all out, but I do have a few of them here. Actually, I think the Wellness Club bought a bunch of these. Bought a bunch of these. They were doing a campaign on how it doesn't matter what you look like. It's it's what you feel on the inside. That's the way Wellness kind of sells their thing, and it's true. Being that I'm going to put this on the internet, I support wellness. All right. So you've seen this type of a mirror here, right, before? See, one of these guys, where you do this type of action. That's fun, right? You know what I mean? So then it's like, whoa, it's huge. And then, oh, just regular me type scenario. And what that is the one that makes your face look huge is slightly concave, very slightly concave. So this is the one that makes my face look huge. So that's concave, just like this is concave, except it's very slightly concave. The focal point for this one's about, 30 centimeters out in front of it. The focal point for this one is probably halfway to the wall there. If you can see your really big face, can you see your really big face in there? It'd be huge. No, you can't. If you can't see it, it means you're probably at the focal point or beyond. All right. So in order to see that effect, you've got to be within the focal point. Remember, when we have an object that's inside the focal point, it results in a larger upright image, and that's what we need if we want to use it as a shaving mirror. All right. So this would just be an absolutely crazy huge shaving mirror, right? It would just be huge, but it would still fulfill the requirements. So you need to put your face within the focal point or within the focal length. All right, so there's our uses of concave. Convex, not very exciting. There is really only one use. And we say that it is a wide angle. All right, we say that it is a wide angle mirror. And I've demonstrated this one, not that exciting, right? Before all the technology of PowerPoints and all that, when I can keep an eye on you crazy kids, right? We had to write on the chalkboard, and then you'd have to turn your back to the students. That puts you in a vulnerable position, right? It's like hunting or being hunted. You never want to turn your back to your prey, right? So you'd try to be like this so you wouldn't turn your back too much. I often thought, you know what I need? I need one of these. And then I could write on the board. I could keep an eye on everybody. That would be safe. That would be the way to go. No, it's not. I know you can see that there's a guy there. No, this is all just the internet. Does it look like me? Taking a picture? No, it's not me. Okay, so I'm just going to jump ahead here for a second because I think I'm done. Yep, I'm going to back up so you can finish writing. So that brings us to the end, really, of our discussion of curved mirrors. I'll put these away. And this is the point where I was gonna plan on doing that little lab, and we're gonna give it a shot. And if it doesn't work, it doesn't work. We'll move on from there. So I'm going to stop my recording. Now, I made a little error when I set up Google Classroom this morning. We're gonna be putting this straight onto our document in Google Classroom, so you can fire up your devices as I stop the recording.